la vérité.
In the previous video, we explored the characteristics of subsonic flow and how information travels through a convergent nozzle. However, a simple convergent design cannot handle the unique physics of supersonic flight. So how is a supersonic nozzle actually designed? And why must its shape constantly evolve during flight? Let's dive into the world of the Laval nozzles and variable geometry. Many mistakenly believe that supersonic power comes solely from the brute force of the turbine. In reality, the engine core only produces angry air, gas at extreme temperatures and pressures. The true transformation from raw energy into staggering speed happens within that seemingly simple pipe at the rear, the nozzle. Even the structurally minimalist ramjet engine, designed for hypersonic flight, is far from a simple straight flame tube. Its very soul lies in the de Laval nozzle. Through the geometric marvel of a convergent-divergent cross-section, the airflow shatters the sound barrier at the throat, and in the divergent section, its internal energy is completely harnessed, converting into an overwhelming surge of super-high momentum. Without the constraints of this specific geometry, even the most furious combustion would result in nothing but futile expansion. Returning to our previous discussion, once subsonic airflow is accelerated to the speed of sound through a convergent nozzle, further acceleration requires the cross-sectional area to expand. To push beyond this limit, the duct must stop contracting and instead begin to widen, allowing the air that has just shattered the sound barrier to accelerate further into the supersonic regime. This specific streamlined profile is the world-renowned de Laval nozzle. To tame the fury of high-pressure steam, Swedish inventor Gustav de Laval proposed a counterintuitive design in 1888. At the time, engineers struggled to boost the efficiency of steam turbines. De Laval realized that traditional convergent nozzles locked airflow behind the shackles of the speed of sound. Thus, he boldly attached an outward expanding bell mouth after the convergent section. This seemingly simple geometric shift unlocked the gas's expansion potential, allowing steam to break the sound barrier in a man-made device for the first time, opening the door to the supersonic era. Today, the de Laval nozzle has long since left the steam factories, entering the fields of aerospace and even industrial micro-applications, such as the familiar fire extinguisher. The coupling of the nozzle inlet to the engine aft section directly defines the flow field characteristics within the Laval nozzle. Given specific modeling dimensions, inlet temperatures of 900 Kelvin and 2000 Kelvin, and standard atmospheric pressure, the system exhibits three distinct operational modes. Among these, the perfect expansion mode delivers the highest aerodynamic efficiency. When the inlet pressure is approximately 543 kilopascals, the throat Mach number approaches the critical value of 1. At this stage, the velocity distribution along the nozzle axis is smooth, with no significant shockwave discontinuities. The exit pressure matches the ambient pressure precisely, the calculated difference being near zero, thereby achieving the optimal state of energy conversion. Based on this, the wall pressure and exit thrust are calculated. Since the exit pressure is nearly identical to the atmospheric pressure, the thrust equation can be simplified as the product of mass flow rate and exit velocity. By analyzing the thrust of a half nozzle, two critical parameters can be derived. The first is the thrust coefficient, which measures the efficiency of the nozzle in converting chamber pressure into thrust. The second is the specific impulse, representing the thrust generated per unit mass of propellant, a key indicator of the propulsion system's propellant efficiency. Under perfect expansion, the thrust coefficient is approximately 1.35, which represents a highly efficient performance level. At an engine combustion temperature of 900 Kelvin, the specific impulse reaches 87.7 seconds, meaning each kilogram of propellant consumed generates approximately 87.7 units of thrust force per unit mass flow. By increasing the total inlet temperature from 900 Kelvin to 2000 Kelvin, the system's specific impulse grew by 48%, reaching 130 seconds. This result quantitatively demonstrates the gain in effective exhaust velocity provided by thermal energy injection. Combined with the high thrust coefficient of 1.35, it confirms that the nozzle maintains excellent aerodynamic expansion efficiency across a wide temperature range, successfully achieving high efficiency conversion from thermal to mechanical energy. These simulation results are highly satisfactory. When the engine exit pressure falls significantly below the perfect expansion benchmark, dropping to 100 kilopascals for instance, the flow becomes overexpanded within the divergent section. To match the ambient atmospheric pressure, strong oblique shocks are generated inside the nozzle, potentially inducing flow separation. This phenomenon creates negative pressure zones along the nozzle walls, which drastically counteracts momentum thrust. Consequently, both the thrust coefficient and specific impulse drop sharply, resulting in a severe aerodynamic efficiency deficit. Conversely, when the engine exit pressure exceeds the perfect expansion threshold, the flow fails to release all its pressure potential energy before reaching the exit plane, entering an underexpanded state. The exhaust continues to expand outside the nozzle, forming distinct wave structures known as shock diamonds. Because a portion of the pressure energy is not converted into axial momentum against the nozzle walls, the thrust coefficient falls short of its theoretical peak for that pressure ratio, resulting in a loss of potential propulsive efficiency. No matter how elegant or scientifically advanced its design, a fixed de Laval nozzle harbors a fatal flaw. Its geometry is static. Every fixed conduit is optimized for only one specific flight altitude and thrust level. Once an aircraft switches from subsonic cruise to supersonic speeds, like the legendary Concorde, or climbs from sea level to 20,000 meters, a fixed-shape nozzle becomes a liability. Unable to adapt to the massive shifts in ambient pressure, its efficiency inevitably plummets. To conquer all altitudes and flight envelopes, engineers have bestowed life upon the nozzle. This is the variable geometry nozzle. By adjusting the throat area, it breathes like a living organism, modulating engine mass flow and back pressure to keep the core performing at its peak. Simultaneously, the synchronized opening and closing of the divergent section aligns the exhaust with the ambient atmospheric pressure in real time. In the governing equations of a de Laval nozzle, the throat area acts as the master gate, primarily regulating mass flow rate and thermodynamic back pressure. Throat expansion. This essentially relaxes flow restrictions to gain a larger mass base, but at the cost of sacrificing the expansion ratio relative to the exit, potentially leading to underexpansion. Throat contraction. By contrast, it builds extreme energy potential through maximum compression. Although the flow is restricted, it empowers each unit of gas with significantly higher expansion potential. In the simulation of variable geometry nozzles, the implicit transient scheme handles Jacobian matrix variations caused by dynamic mesh updates more robustly through inner iterations within each time step. This ensures computational stability in regions with high Mach number gradients, such as the throat. By comparing the wall profiles of the fixed geometry versus the morphed configuration, the change in the throat's cross-sectional area is clearly visible. The morphing formula is centered on the lowest point of the throat, driving a synchronized deformation of both the converging and diverging sections. This coordinated adjustment strategy ensures a smooth transition of wall curvature, thereby enhancing flow field stability during the computation. The inlet pressure and temperature used here are kept consistent with the values from the undeformed, perfectly expanded state. This ensures a clearer comparison of the numerical variations following the deformation. Using the Python API, we can extract and process star CCM results in real time. Here, we present 3 sets of comparisons between the pre- and post-deformation states, starting with the Mach number distribution at the exit. As the throat contracts, the mass flow rate decreases. The flow in the divergent section shifts from perfect expansion to overexpansion, causing further acceleration of the gas, while the pressure drops even lower. Due to the combined effect of reduced mass flow and increased negative pressure at the exit, the total thrust actually decreases. Next, let's examine the changes in Mach number and pressure at the throat. Due to the contraction, the original radius of 0.3 meters has been reduced to 0.23 meters. Here, we can clearly see the loss of data points corresponding to the modified width. At the same time, the local values remain largely unchanged, maintaining a Mach number close to 1. Finally, let's look at the Mach number and pressure variations along the nozzle centerline. Within the nozzle, specifically the range under 0.9 meters, the Mach number increases steadily, reaching nearly 1.0 at the throat and approximately 2.0 at the exit. Since the initial simulation represents a perfectly expanded state, the velocity and pressure downstream remain relatively stable, with no significant jumps or shock waves. However, as the throat area changes, the flow in the divergent section accelerates further. Approximately 0.5 meters beyond the exit, a distinct velocity jump occurs. This is a shock wave. Simultaneously, we observe a sharp spike in pressure. This is the physical manifestation of the Mach diamond phenomenon. Modifying the exit area directly alters the expansion ratio, which dictates the freedom of the airflow after leaving the throat and locks the equilibrium between exit Mach number and static pressure. When the exit overexpands, the flow gains a luxury of expansion space, causing velocity to surge at the cost of a plummeting static pressure. Once the exit pressure falls below ambient, it triggers overexpansion. Shock waves migrate upstream inside the nozzle, potentially leading to severe boundary layer separation, causing thrust efficiency to collapse instantly. When the exit expansion is restricted, the flow is trapped in a narrow passage, resulting in underexpansion. This means a vast amount of internal energy, which should have been converted into kinetic energy, is discharged prematurely. The high temperature, high pressure gas expands explosively outside the nozzle, leaving behind brilliant but regretful shock diamonds. Before and after the exit deformation, the various physical flow properties at the throat remain almost unaffected. The Mach number at the center of the exit shows a significant increase, whereas the increment near the edges is less pronounced. Due to the pre-deformation sampling points being in the ambient stream influenced by the nozzle wake, the Mach number there hovers around 0.6. Along the center line, as the deformation increases, the Mach number at the exit increases slightly. However, the velocity stability outside the nozzle decreases, leading to larger fluctuations in the Mach number. In reality, the final increase or decrease in thrust isn't just a linear addition of surface area. Instead, it's a dynamic balance between mass flow rate, exhaust velocity, and pressure matching. Essentially, the result of dynamic deformations at the throat and the nozzle exit. This is exactly what I'll be diving into in our next video. See you then.